I'm going to present our work on the RHINE naming system. This is joint work with a group of colleagues from ETH Zürich. DNS is commonly known as Internet's phone book, but it has evolved into a quite versatile system that supports various applications like load balancing. And a lot of things are happening in DNS regarding security. For example, several cache poisoning attacks were disclosed recently. Some of them use sophisticated side channels that are unknown before. And people also find clever ways to take over domains and their name servers by, for example, making use of stale DNS records. So this kind of DNS attacks really have a profound impact on the entire internet because they enable attacks on many other protocols like the web, timesync, VPN, etc. On the defensive side, we're also seeing increasing deployments of DNS over secure transport between a client and recursive resolver. There are also plans to protect the communication between a resolver and authoritative name server. But the problem with secure channel is that they do not provide end-to-end data authenticity. Right? The client has to trust all the servers, but any one of them could manipulate data, which is not uncommon in reality, by manipulators from both within and outside DNS ecosystem. Another more canonical approach is DNSSEC. It allows zone owners to cryptographically sign their data in an offline manner and establish a key hierarchy along with a delegation hierarchy. This would, in principle, allow a client to verify a DNS answer by following an authentication chain all the way up to the key of the root zone without trusting any DNS servers. However, even after years of deployment, the adoption rate of DNSSEC is still quite low. It's estimated that only a small fraction of DNS of domains are signed, and 1/3 of users are somewhat enjoying the security benefits. But the tricky part here is that it is not the end users that do data validation, but instead recursive resolvers, right? So a client or end user simply rely on a single bit in the response from a recursive resolver, indicating whether the data is being validated or not. So in practice, DNSSEC also fails to provide end-to-end guarantee. And why this is the case? Well, one of the main reasons is that DNSSEC is really complex to implement and operate. Any inconsistency on a delegation chain, for example, mismatching key or algorithm, would result in validation failure. There's actually a nice website listing all those major DNSSEC outages. It's quite impressive to see from there how frequently this outage happens and how people are struggling with getting DNSSEC right. So the limitations of this approach has motivated us to rethink the problem of authentication in DNS. What we want is really end-to-end data authentication, where one end being the client and the other end being zone owner. And a solution, authentication mechanism, has to be as simple and robust as possible, and also backward compatible to be usable. Our key observation is that there are actually two things to be authenticated in DNS: zone delegation and zone data. And they are treated the same by DNSSEC. What we can do is to decouple these two and introduce external CA to certify the delegated authority of the zone. This would allow the owner of the zone to sign this data with a certificate, and the client who already trusts the CA to easily verify the data signed using the certificate. Another benefit is that a zone, once delegated, does not need to synchronize its parent. Right? It can independently manage its security without being affected by the potential misconfiguration of its parent. Despite these benefits, this architecture also raises a new problem. One obvious problem is that, do we get better security by trusting CA instead of DNS authority? The answer might be no, because a malicious or compromised CA could issue certificates for arbitrary zone, which is not the case in DNSSEC. Right? And the less obvious problem is that how do we bootstrap security in the first place? Right? So before issuing a certificate, a CA must verify that the requester indeed owns the zone or domain. And this is typically done through a challenge response process, which, however, relies on DNS. And so it could be exploited by the attacker to obtain a fraudulent certificate. What this means is that we'll be running into a security dependency, right? We'd like to use a certificate for the authentication of a zone's data, but the secure issuance of the certificate requires the zone to be authenticated in the first place. And this kind of subtleties has to be handled very carefully to avoid security vulnerability. So in RHINE, we have systematically addressed these issues, and in particular, we created a robust trust model where different entities watch over each other, so no single party could compromise a zone's authority. To achieve this, we introduced a new public login mechanism called Delegation Transparency that keeps track of the delegation status of the entire namespace. This is actually necessary to prevent certificate misissuance and to protect a zone from being attacked by a potential malicious parent. And conceptually, the operation of RHINE could be divided into two parts, online and offline. And the complexity of authentication could be shifted to the offline stage, where most operational errors could be handled without impacting the online name registration process. So we have defined a set of protocols to specify RHINE's functions. I will introduce 3 of them here. So to set up a secure delegation, the owner of a new zone first asks for an approval of delegation from its parent. It then sends a request to a set of selected trusted entities, including one CA and several DT loggers. They will cross-check with each other for the validity of the request and each other's attestation. If everything's okay, then a certificate will be issued to the new zone. And an important point here is to have the parent approve the delegation, because before the delegation is established, the parent still legitimately owns the child zone, right? And with this, the approval of delegation actually could serve for ownership validation. And of course, the parent itself has to be established and certified beforehand, perhaps by a different CA, and this could go all the way up to the top of the namespace. And there we have the root zone certified itself, and then directly certify top-level domains, right? And in this way, we build an implicit authentication chain in an offline manner for zone delegation. And once the zone is established, it can update its delegation parameters. For example, its public key by interacting with its trusted entities, right? And the point here is that this can be done independently of the zone's parent, and in most cases. As a result of the setup and update operations, DT loggers will receive streams of requests, and they should periodically synchronize with each other to maintain a consistent log. And for this, we have adopted and enhanced a secure consensus protocol that is optimized for log replication and formally verified. So as you may imagine how hard it is to analyze the security of RHINE manually, because different entities could interact with each other in subtle ways that can break security. So we have spent a lot of effort to formalize the RHINE protocols using Tamarin, which is a state-of-the-art automatic verification tool that has been applied in many real-world security protocols. And this has really helped us to identify multiple design flaws in the early version of the protocols. And the main property we verify for RHINE is that once the zone is delegated, its data cannot be forged even by a powerful adversary that can control the entire communication network and the entire name resolution infrastructure, as well as the potential malicious parent and all trust entities except one logger, right? So this is arguably the strongest possible data authenticity guarantee we could obtain for a hierarchical naming system. To see the deployability of RHINE, we could compare its operation with existing approaches. For example, for end users, RHINE requires the maintenance of trust store and the verification of certificate. And this function has been implemented in many operating systems and applications like browsers, right? So the deployment for end user is actually quite comparable to Duan dot. The operation of recursive resolver in RHINE is actually simpler than that in DNSSEC because there's no need to process an error-prone authentication chain. And authoritative name servers in RHINE and DNSSEC are quite similar, just to serve security-related records whenever requested. And actually, RHINE could reuse several types of security records of DNSSEC and some of the processing logic as well. And finally, for zone owners, RHINE is simpler because there's no need for a zone to synchronize its key materials with its parent. And this is done mostly in different ad hoc ways by DNS operators today. So to summarize, RHINE is compatible with existing DNS infrastructure, and it could coexist with Duan dot to provide both data authenticity and privacy at the same time. The offline part of RHINE is also compatible with today's Web PKI because the zone owners and CAs are interacting to interact with each other for their issuance and management of certificate. And this is automated by our well-defined RHINE protocols, and they could also be integrated into the growing Acme ecosystem. And finally, for the logger, the function of delegation transparency requires a bit more actual effort to deploy because it's quite different from CT. But what we envision is that in the initial stage, we could have a small set of highly reliable CT loggers to implement DT functions, and we can expand the base gradually. We developed a prototype of RHINE, and the online part is based on existing DNS software, including SDNS and Core DNS. And we measure the performance of the resolver in a realistic setup with a cache hit ratio of 80% for client queries. And it's not, from the result, you can see that actually the overhead of RHINE is actually much lower than DNSSEC. This is not surprising because DNSSEC requires the processing of a longer authentication chain that could go wrong. For the offline part of RHINE, we find that the overall performance is actually determined by the DT consensus process. But our streamlined RHINE protocols can already issue 20 million of certificates per day, even on commodity servers. And in comparison, in today's Web PKI, 6 million of certificates are issued per day. So that means the offline part of RHINE could also practically operate at internet scale, right? And for more evaluation results, please refer to our paper. Okay. So to conclude, we believe that a secure internet necessarily needs end-to-end secure memory solution, which is unfortunately not provided by today's DNS infrastructure. And we hope RHINE could improve the status quo by enabling a robust end-to-end authentication with strong guarantee. As next step, we plan to deploy RHINE in different environments, including integration into browser. And also, importantly, we also plan to improve the availability aspects of RHINE with Cyan, which is a next-generation internet architecture that can guarantee highly available communication even under massive DDoS attacks. Actually, the successful deployment of Cyan in more and more production networks has proved that it's possible to incrementally upgrade today's internet with strong security property. And we hope the internet could also benefit from RHINE as well. So I'll stop here, and thank you very much for your attention. Be happy to take questions.